You can take the heading of hemoglobin. Yesterday I have explained about hemoglobin. You just note down a few points about hemoglobin. Stool. Write down. First, deoxyhemoglobin. Deoxyhemoglobin. In deoxyhemoglobin, subheading geometry. Geometry. Deoxyhemoglobin, in that again subheading is geometry. You can just draw this. Porphyrin, instead of giving the full ring, I am just giving it as 2 blocks. From side view, it is like a 2 blocks. Suppose if this is 1 nitrogen, second, third and fourth. This is a full porphyrin that we draw. But if I am looking it from a side, it is just like 2 blocks. And it is not exactly plane, but it is out of plane. It is being pulled. Because it is deoxy form, iron is not in the plane of porphyrin. Okay, so you can just imagine this as porphyrin. The porphyrin is not in plane, it is coming out of the plane. Iron is coming out of the plane. And what is the distance between the nitrogen and the iron of porphyrin? These are the nitrogens. It is about 2.01 angstroms. And the distance between the porphyrin nitrogen and the nitrogen of your histidine, it is about 2.7 angstroms. If I can just draw oxy, you will be knowing it. You can draw this later, but you just compare both. What difference do you find? Yesterday we have drawn it in a different way, right? Iron is outside the plane of porphyrin. Iron is outside the plane of porphyrin. Iron is outside the plane of porphyrin. And that porphyrin is not in plane. It is just like puckered one. It is pulled. This iron is pulling it. And the pulling effect, distance will increase from this nitrogen to this iron. From this nitrogen to this nitrogen is about 2.7 angstroms. Distance is more. It means it is going away from this porphyrin nitrogen. Whereas in this case, iron is moving inside. So this nitrogen will come little close and the distance is found to be 2.1 angstroms. 2.1, this is 2.7. So this is lengthier. This is also little lengthier, 2.01, 1.989, not much difference, a very little difference. So first write about deoxy, then we'll go towards oxy. Geometry, geometry, distorted square pyramid, distorted square pyramid or distorted tetragonal or tetragonal square pyramid. Tetragonal square pyramid or tetragonal pyramid or distorted octahedra. Octahedra when solvent molecule is considered. Distorted octahedra. In bracket you put solvent molecule, water. When water is also considered, it will be 6 coordination number. Next point. Coordination number 5. Coordination number 5 dash 6. If solvent is considered, 6. If solvent is not considered, 5. Coordination number 5 or 6. Next. What are the coordinating ligand atoms or the donor atoms? First one, nitrogen of porphyrin. Second is also nitrogen of porphyrin. Altogether 4 nitrogens from porphyrin. Fifth one is a nitrogen coming from histidine. Sixth one, which is an optional, oxygen coming from a water molecule. So these are the donor atoms. 5 nitrogen atoms, 1 oxygen atom. 5 nitrogen atoms if I don't consider any solvent, only nitrogen rich environment. But even if I consider a water molecule oxygen, it is still nitrogen rich environment. 5 nitrogens, 1 oxygen. When we look at the biochemistry, we have a chemical called as biphosphoglycerate or diphosphoglycerate. What is the importance of this chemical? I'll just tell you. Maybe it is not that useful in your chemistry, but you just try to understand what will happen. This is a porphyrin. In this porphyrin, iron is not in the plane of porphyrin. It is coming out of the plane of porphyrin. And yesterday I told you there is a space inside the porphyrin. What is the size of the space? It is anywhere around 80 picometer. So whenever the iron is not in the plane of porphyrin, that space will be occupied by a chemical called as 2,3-diphospho or biphosphoglycerate. Generally we say solvent molecule will come and bind. But there is also some other biomolecule which can come and sit in that place. And what is that molecule called as? 2,3-BPG or DPG, diphospho or biphosphoglycerate. So that molecule will come and occupy that space. Whenever dioxygen is ready to come, this 2,3-BPG will go away. Once 2,3-BPG goes away, there is a vacant space. That will create a driving force for iron to take up dioxygen. Did you get the point? Suppose dioxygen is coming, right? Iron is present. Slowly dioxygen is coming. This iron must bind to dioxygen. There should be some driving force. What is that driving force? You are standing in a bus stop. You don't want to come to institute. Will you get into the bus? You will simply sit there for a longer time. But at 2 o'clock there is a class. Then you are at bus stop. So the time of your class will be the driving force for you to enter into the bus. Yes or no? So there should be some driving force for you to come to the institute. There is a class, therefore you come. Likewise, there should be a driving force for the dioxygen to come and bind with the iron. What is that driving force? That driving force is unbinding of 2,3-DPG. So whatever space that is present, in that space 2,3-DPG will be present. Once that 2,3-DPG goes away, it creates a vacant space that will create a driving force for the incoming dioxygen to take. Okay? You might have heard about fetal hemoglobin and mother hemoglobin. What is the difference? Mother hemoglobin is different from fetal hemoglobin. Any mother who is pregnant, suppose her blood has to go into the oxygen present in the blood of the mother, if it has to go into the fetus, there should be some driving force. What is that driving force? It is again the 2,3-BPG. Whatever hemoglobin that the mother has, in that deoxy form, 2,3-DPG will be binding. Fetal hemoglobin will also have same 2,3-DPG, but its binding will be weak. It will not bind strongly. Since it does not bind strongly, it can easily unbind. Once it unbinds, it creates a space. Into that space, some other molecule must come and bind. That is our oxygen molecule. So once the mother hemoglobin is taking up the dioxygen, fetal hemoglobin has to take that dioxygen easily. Because fetus is not ready to take forcibly. There should be some other driving force. That driving force is weak binding of 2,3-DPG. DPG does not bind strongly, it easily unbinds. Once it easily unbinds, it creates a space. That space will be occupied by the dioxygen coming from the mother hemoglobin. So that is the difference between mother hemoglobin and fetal hemoglobin. We simply say that fetal hemoglobin has a greater affinity towards dioxygen. That is the reason, though the fetus is in the womb, still they take oxygen from the mother. We are anyway inhaling. But how does the fetus inhale? There is no respiratory system by that time. This is the mechanism. Okay? So there is a driving force that creates to take up dioxygen coming from the, what you call, respiration. You just note down that point. This is just an additional point. The space present in the core, CORE, the space present in the core of porphyrin, the space present in the core of porphyrin is occupied by 2,3-DPG or BPG, biphosphoglycerate or diphosphoglycerate. Is occupied by 2,3-DPG or BPG. The unbinding means going away. The unbinding of 2,3-DPG, the unbinding of 2,3-DPG creates a driving force, for dioxygen binding. Dioxygen means O2. Creates a driving force for O2 binding. Creates a driving force for O2 binding. O2 binding. Next. There are different types of distortions. There are different types of distortions present in deoxyhemoglobin. There are different types of distortions present in deoxyhemoglobin. These are tetragonal distortions. These are tetragonal distortions and rhombic distortions. These are tetragonal distortions and rhombic, RHOMBIC, and rhombic distortions. Next point. The geometry of deoxy-HB, can be considered as an elongated octahedra. Can be considered as an elongated octahedra. This gives 4 energy levels. This gives 4 energy levels. Okay. Now just listen, if at all any question appears, what are the different types of distortions that are found in deoxyhemoglobin? We said there are two different types of geometries. One is tetragonal or square pyramid, distorted square pyramid. Second one we call it as octahedra, but distorted octahedra. In that distorted octahedra, there is a distortion. So at the sixth coordination site, there is no ligand. Though there is a ligand, it is water molecule, it is weakly bound. So along the axis, along z-axis, the ligands are weakly bound. I can imagine it to be a elongated octahedra, because along the z-axis the bond is not strong, it is weak. So I consider it as elongated octahedra. Therefore, we never say that the geometry is a perfect octahedra, we say distorted octahedra. That distortion is due to elongation, tetragonal distortion. So due to that elongation, T2G and DG is further splitting into 4 different energy levels. Okay, so this is elongated octahedral splitting, right? Next point, can you just imagine this as porphyrin? All this porphyrin has got a pi electron density. That pi electron density is a delocalized cloud, conjugation is continuously happening. Inside is a iron. Iron has got 2 different sets of orbitals, EG and T2G. T2G has pi symmetry. It means it can form a pi bond. So that T2G orbitals means dxz, dyz and dxy. These lobes, can you just imagine if this is a pi delocalization cloud of the porphyrin, here we have some orbitals of iron. These orbitals have got a pi symmetry. This is pi symmetry, this is also having some pi symmetry. Both are same symmetry. They interact with one another. But this interaction is not symmetric. It is not favorable, it is unfavorable. Are you getting my point? There is a pi delocalization cloud occurring in the porphyrin. Okay, this can form pi symmetry. Even in this iron metal, there are some orbitals. Which orbitals? dxy, xz and yz. It also has got some pi symmetry. So this pi symmetry, this pi, they can interact with one another. But the interaction is not symmetric, it is unfavorable. Because iron is not present in the plane, iron is below. Once I say iron is below, suppose if these are the 2 lobes of T2G orbitals. Out of 4, one is above, one is below. So one will interact with this pi electron density, one will not interact. Okay, so it is unsymmetric interaction. Are you getting the point? Just suppose if this is porphyrin pi electron cloud, where is the iron? Is it present in the center? No. If it is present in the center, 1 lobe, 2 lobe, 3 lobe, 4 lobe, it will interact symmetrically. But that iron is not present in the center, that iron is somewhere here. So if I say 1 lobe, 2, 3 and 4, these 2 lobes are interacting, but these 2 lobes are not interacting. So it is called as unfavorable orbital interaction. This pi, both are having same symmetry, but interaction is unfavorable. Due to this unfavorable orbital interaction, you have further splitting. And this splitting we call it as rhombic splitting or rhombic distortion. So if any question appears, what are the types of distortions you find in deoxyhemoglobin? 2 types. One is tetragonal distortions, another one is rhombic distortion. Tetragonal distortion is appearing because it is not a perfect octahedra, it is a distorted octahedra. Along the z-axis there is a water molecule which is weakly bound, therefore we consider it as an elongated octahedra. Next, porphyrin has a pi electron cloud which has unfavorable orbital interactions with the T2G of the iron. Due to that unfavorable orbital interaction, there is a further distortion which we call it as a rhombic distortion. Further splitting will occur. Okay. So how many electrons are there altogether? How many electrons? 6. Iron 2. So 6 means 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5 and 6. And that same thing will continue. So altogether how many unpaired electrons? 1, 2, 3, 4 unpaired electrons. Okay. You can just draw this diagram. Can you just look at this? Do you find any orbital angular momentum? Yes, xz and yz. but due to this rhombic interaction, even that is lost. Rhombic distortions, even that is lost, but still the magnetic momentum is found to be 5.45. So there are some things which cannot be explained properly. In the last class I told you magnetic momentum is 5.45. So when I say 5.45, definitely orbital angular momentum should also include into spin angular momentum. But due to rhombic distortions, we show the splitting of these two orbitals. Then orbital angular momentum should also stop. You should get around 4.9, but still you have 5.45. So there are few things which cannot be properly explained. You need not remember the diagram, but you have to remember two types of distortions: tetragonal, where it is an elongated, and rhombic distortions. Tetragonal distortion is due to weak bonding, 6th coordination site. Rhombic distortion is due to unfavorable orbital interactions with the porphyrin pi cloud and the T2G of the iron. You may write down that point once you draw the diagram. This could be XZ or YZ. Just you may write this as YZ, XZ, no problem. Only I have shown the splitting. So which one is below? It is exactly unknown. Right. Tetragonal distortions are due to weak bonding. Tetragonal distortions are due to weak bonding at the 6th coordination site. Tetragonal distortions are due to weak bonding at the 6th coordination site. 6th coordination site. Next, rhombic distortions are due to unfavorable orbital overlapping interactions, between the pi electron cloud of porphyrin and the T2G set of iron. T2G set of iron. Okay. So that is about the geometry. What point you have to remember? Geometry. Distorted square pyramid is one geometry when solvent molecule is not considered, or tetragonal square pyramid or tetragonal pyramid. All these are different names given. If at all a solvent molecule is also considered, we call it as a distorted octahedra. In that distorted octahedra, you have elongated distortions or elongated octahedra. Further, unfavorable pi interactions is giving you rhombic distortions. Right? This is about geometry. Next, magnetic aspects. This is also for deoxyhemoglobin only. First we will complete deoxy, then we will move to oxy. Magnetic aspects. There are 4 unpaired electrons. Next, expected magnetic moment. Expected magnetic moment 4.9 bm. 4.9 Bohr magneton, but found is 5.45 bm. 5.45 bm. This is according to Pauli. According to Pauli, it was found to be 5.45. Next point. Deoxy-HB is paramagnetic. Deoxy-HB is paramagnetic. So 2 points you have to remember regarding magnetic aspects. It is paramagnetic. Magnetic momentum is 5.45, not 4.9. Deoxy-HB is paramagnetic. Next. Electronic aspects. Geometrical aspects is completed. Magnetic aspects. Third one is electronic aspects. Electronic aspects. Deoxy-HB is purple colored. Deoxy-HB is purple red. You may call it as purplish red. Purple, P-U-R-P-L-A. Purple, purplish red. Purplish red color. This is due to pi to pi star. This is due to pi to pi star intraligand charge transfer transitions. This is due to pi to pi star intraligand charge transfer transition. Intraligand charge transfer transition. Next. There is no evidence for DD transition. There is no evidence. There is no evidence for DD transition. There is no evidence for DD transition. Okay. Though you find unpaired electrons, but no DD transition was there. No evidence for DD transition. Next. Absorption spectra. Absorption spectra has two bands. Absorption spectra has two bands. One at 555 nanometer. One at 555 nanometer called as Q band, capital Q. One at 555 nanometer called as Q band, and another at 400 nanometer, and another at 400 nanometer called as SORAT band. S-O-R-A-T, SORAT band. SORAT band. Next, SORAT band. SORAT band is 10 times more intense. SORAT band is 10 times more intense than Q band. SORAT band is 10 times more intense than Q band. Then you write subheading oxyhemoglobin. Oxyhemoglobin. You draw that diagram. Iron should be in the plane of the porphyrin. Above you have a distal histidine. Below one is called as a proximal histidine. Hydrogen bonding also you can show from the distal histidine hydrogen with the dioxygen. Iron dioxygen is not linear. It is bent nearly 131 angle. So few additional points will come in the geometry of oxyhemoglobin. Every point is a important point. Previously 2.7 angstrom distance between the two nitrogens has now dropped to 2.1. It means it is going inside. Iron is going inside. Previously it was that much outside, 0.6 angstrom outside. Now it is moving inside. Subheading geometry. Geometry. Perfect octahedra. Perfect octahedra. Perfect octahedra. Next, coordinating ligands. Coordinating ligands. Write down 4 nitrogens from porphyrin. 5th nitrogen from histidine, and 6th one is an oxygen from dioxygen. Oxygen from dioxygen. Not both oxygens are bound, only one oxygen from dioxygen. Both oxygens bound, that was a failed model. There was another model where iron will bound to both oxygens, but it is a failed model. You should not show such a bonding mode. 1, 2, 3, 4, 5 nitrogens and 1 oxygen. In deoxy also 5 nitrogens, 1 oxygen from water, 5 nitrogens, 1 oxygen from dioxygen. There is a difference. Okay, take down the point. 4 coordination sites. 4 coordination sites are occupied by 4 coordination sites are occupied by nitrogens of porphyrin. Nitrogens of porphyrin. Nitrogens of porphyrin. Next, 5th coordination site. 5th coordination site is occupied by 5th coordination site is occupied by nitrogen of imidazole of histidine. Directly histidine also you can write, but further you write down nitrogen of imidazole of histidine. Nitrogen of imidazole of histidine. Next, 6th coordination site. 6th coordination site is occupied by O2. 6th coordination site is occupied by O2. Next, most important point, bonding mode of O2 is, what is the bonding mode? Bonding mode, end on terminal. Bonding mode of O2 is end on terminal. In the last class I told you, metal, oxygen, this is called as end on terminal. Bonding mode of O2 is end on terminal. Very important point, many times asked question. GATE, CSIR, SET, everywhere it has appeared. Next, the bond angle is around 131 degree. The bond angle is around 131 degree. Okay, so this one 131 to 133 it can range. Next, depending on the organism, the bond angle ranges from, depending on the organism, bond angle ranges from 115 to 155. Depending on the organism, bond angle ranges from 115 to 155 degree. 115 to 155 degree. Next, the stability, this is another important point. The stability for iron dioxygen binding, the stability for iron O2 binding comes from hydrogen bonding, where the hydrogen of distal histidine is involved, where the hydrogen of distal, DISTAL, where the hydrogen of distal histidine is involved. Hydrogen of distal histidine is involved. Distal histidine is involved. Okay, so that is about geometrical aspects. Next, magnetic aspects. Magnetic aspects. Oxyhemoglobin is diamagnetic. Oxyhemoglobin is diamagnetic. There are different proposals. There are different proposals of iron and oxygen. There are different proposals of iron and oxygen. These are first you look and then you can write. In the last class I told you two different proposals. The most accepted one is iron 2 low spin, iron 3 low spin. If it is iron 2 low spin, dioxygen is present in a triplet state, but the triplet state should be converted into singlet state. Only then it will be diamagnetic, or else you cannot explain why the oxyhemoglobin is diamagnetic. Okay, so first proposal, iron 2 low spin, dioxygen not in a triplet state but it is in a singlet state. So there has to be a conversion from a triplet into singlet. Even if you go to 2009-2010 GATE exam questions, in that GATE exam also they have considered the same proposal. They have considered oxyhemoglobin as iron 2 low spin, but later GATE exam, again you can watch, they have considered it as iron 3 low spin. So the same GATE exam, once they considered iron 2 low spin, later they considered iron 3 low spin. You look at previous set exam questions. In set exam they will give you iron 2 low spin. They are still considering the old GATE proposals. But you always remember, according to the new data, it is iron 3 low spin. Okay, yesterday I have given you some evidences also. What are those evidences? One is stretching frequency around 1050 wave numbers. It is very close to that of superoxo. And XPA's data 3.2 oxidation state for iron, which is close to 3 but not 2. So two strong evidences. So this proposal we are anyway neglecting it because it requires energy for triplet to convert into singlet. There is no proper explanation for it. Second proposal, iron is present in +3, then that electron is going into oxygen. Oxygen is converting into superoxo. O2 is superoxo. So in this O2 superoxo, there is one unpaired electron, and iron 3 there is one unpaired electron. These two will undergo strong antiferromagnetic coupling that will lead to diamagnetism. That is our next proposal. Third proposal is iron is present in +4, which is a rare oxidation state. Iron +4 means 4 electrons, and those 4 electrons will be paired up. Okay, don't put 1, 2, 3, 4, but they will be paired up because iron is present in +4, very strong. And O2 is present as O2 2 minus, peroxo form. So again no unpaired electron, therefore it is diamagnetic. That is a third proposal. But iron from +2 entering into +4 requires a greater energy. So it requires a lot of activation energy which is not available at hemoglobin level. Therefore iron 4 proposal is also neglected. Iron 2 proposal is also neglected. Finally we are going with iron 3. Okay. You write down all the 3, but evidence you write down for the second one. Take down the evidences. First you write down the proposals, then the evidences. First one, iron 2 low spin, oxygen converting from triplet into singlet. It is not a triplet oxygen, it has to be a singlet. Only then it will be diamagnetic. Second proposal, iron 3 low spin, oxygen as a superoxo. Third proposal, iron 4 low spin, oxygen as peroxo. Don't draw this now. This is for second proposal. 1, 2 and 3. Next, write a point. Iron 2 and iron 4 low spin states, iron 2 and iron 4 low spin states are ruled out, RULED, ruled out, neglected, are ruled out because of high energy involvement, are ruled out because of high energy involvement, high energy involvement. Next, for iron 3 low spin, the combination is, write down this. For iron 3 low spin, the combination is, write 5 electrons, put 1 up spin, superoxo, put 1 down spin, make them close so that you can experience a strong antiferromagnetic coupling. Then you can write down, there is a strong antiferromagnetic coupling, there is a strong antiferromagnetic coupling, there is a strong antiferromagnetic coupling due to which oxyhemoglobin behaves as diamagnetic. Okay, oxyhemoglobin behaves as diamagnetic. So two important points to remember with respect to magnetic moment. It is diamagnetic, and diamagnetism is due to antiferromagnetic coupling. So what is the magnetic momentum? 0. There is no magnetic momentum, it is 0. Last, electronic aspects. Oxyhemoglobin is red color. Next, two peaks appear in the electronic spectra. One at 451 and another at 476 nanometer. 451, 476 nanometer. Next, reason for color is pi to pi star ILCT, and interference of iron O2 bonding, iron oxygen bonding, interference of iron O2 bonding. So interference means, in some books it is given as LMCT, from oxygen to iron. So there is some charge transfer transition but there is no direct evidence of a DD transition. ILCT is always there because porphyrin is present. Along with that, there is an interference of iron oxygen binding. Okay, so geometrical aspects, magnetic aspects, electronic aspects of deoxyhemoglobin as well as oxyhemoglobin, all are completed. Okay. Write down next point. Just write a question. What is the molecular weight of hemoglobin? What is the molecular weight of hemoglobin? What is the molecular weight of hemoglobin? Write down the options. 17.5, 34, 64.5, 72.2 kilodalton. KD refers to kilodalton. KD, kilodalton. DALTON, Dalton. Kilodaltons. Any answer? 17 is for myoglobin. I have given you a hint. Anywhere around 17 is for myoglobin. So how much could be for hemoglobin? I have given you a hint. Myoglobin is a monomer. Hemoglobin is a tetramer. So if myoglobin is around 17, how much will be hemoglobin? C. 64.5. Though you multiply with 4 times, you will not get this, but it will be close. Because myoglobin, the number of amino acids will be more. 153 amino acids will be there. Whereas in hemoglobin, you will have only 141 and 146, alpha and beta. In this case, you have 153 for hemoglobin. Write down 64.5 or 64,500 Dalton. 64,500 Daltons. So how much is the molecular weight of hemoglobin? 64,500. Is it a small molecular weight or large molecular weight? Very large. Suppose if I ask you what is the molecular weight of water, you say 18. And what is the molecular weight of hemoglobin? 64,500. So if I ask you to prepare 1 molar solution of hemoglobin, how much of hemoglobin is required? Very high amount. If I ask you to prepare 1 molar 1 liter solution of hemoglobin, it requires lot of hemoglobin. So this is the reason it becomes very difficult for us to study about hemoglobin in the lab. Every time I have to isolate, if I want to prepare a molar solution, I need more number of hemoglobin. I require more amount of hemoglobin because the molecular weight is very, very high. Okay. We'll just take a 5-minute break. Then we'll continue with the other aspects. How hemoglobin binds with dioxygen, cooperativity, all those things. But again, you just write a question, a general question or a general point. The affinity AFFINITY, the affinity for fetal hemoglobin, the affinity for fetal hemoglobin towards O2 is high when compared with mother hemoglobin. When compared with mother hemoglobin. This is due to what is the reason? Weak bonding of, this is due to weak bonding of 2,3-DPG weak bonding of 2,3-DPG with hemoglobin. Weak bonding of 2,3-DPG with hemoglobin. Okay. Next, you just write a question. Who are blue fugates? Who are blue fugates? Blue fugates. We'll just take only 5-minute break. If possible, I'll continue till 3:45 or 3:50. Okay. Anyone search for blue frigates? You got the answer? Anyone? Blue frigates. Okay, where is this family from? West Virginia. Exact place? Maybe there it is given as West Virginia, but there is another place. Okay, I'll give you a hint. Everyone is aware of KFC. But what is that KFC? Kentucky. The place is Kentucky. So there they have started this fried chicken. They call it as Kentucky Fried Chicken. And these blue frigates, these people are also related to Kentucky place. What is the importance of these blue frigates? There is an anomaly which is associated with these blue frigates. Usually what happens is, in every human being, whatever hemoglobin that is present in me, there are 4 subunits. I told you that one iron will not interact with the another iron. If at all they interact, then the oxygen will lose its reversibility and finally the person will die. But even though globin chain is protecting our hemoglobin, every time nearly 3% of hemoglobin will convert into hematin. You might have heard about hematin. We'll discuss about that. But every day, every time 3% will be converting into hematin. Right? But that hematin will be back converted into hemoglobin by an enzyme called as diaphorase. The enzyme name is diaphorase. It is also called as methemoglobin reductase. But in these people called as frigates, it is a family. Frigates is a family. So in them, this diaphorase enzyme does not work. Once this diaphorase enzyme does not work, what happens is, every time hemoglobin will be converting into hematin, back conversion is not possible. Once back conversion is not possible, those persons will die. And those babies or blue frigates, they call it as blue because the blood will be looking like blue from outside. It will lose the oxygen binding capability and finally the persons will die. There is one medicine for them. That medicine is methylene blue. You might have heard about this. Methylene blue is a dye, just like phenolphthalein, methylene blue. It is also used as an indicator, methylene blue. Okay, it is used as a dye. So this methylene blue is given to those people which will act as a function of diaphorase. Whatever function diaphorase is doing, the same function is also done by this methylene blue. So due to this methylene blue, these people can survive. And this anomaly was found in this family only. That is the reason they were called as blue frigates. Frigates is that name of that family who lives in Kentucky. Okay. So this is how blood is correlated to many anomalies also. Okay. Write down a point. Blue frigates. These are a family. These are a family where these are a family where the hematin, Hematin, hematin does not convert back into hemoglobin. Hematin does not convert back into hemoglobin because of absence of an enzyme called as diaphorase. Because of an absence of an enzyme called as diaphorase. Absence of an enzyme called as diaphorase. Such people die soon. Such people die soon. Next. Methylene blue can perform the job of diaphorase. Methylene blue can perform the job of diaphoresis. Next, subheading cooperativity. Expected rate of stability constant, it will be decreasing. I am expecting it to decrease, but it is increasing a lot, and the reason for the increase is cooperativity. It is just like your group studies. Singly you are studying, efficiency will be little less. Group study, suddenly efficiency increase. Provided you are studying properly, efficiency will increase. Any reason for it? Group discussion, it is just like constructive overlapping. Constructive overlapping, therefore efficiency will increase. The same thing will also happen here. Yesterday I have explained you, one iron takes up dioxygen, that will trigger the taking of the another dioxygen. These two trigger the taking of third, these three trigger the taking of fourth. That mechanism is called as cooperativity. First write down the reactions, I will give you the points. The stability constants increase. The stability constants, K refers to stepwise stability constant. In last unit I have told you stability constant. The stability constants increase due to a process called as, the stability constants increase due to a process called as cooperativity. Cooperativity. Next, cooperativity is a relay mechanism. Cooperativity is a relay mechanism. It means one will come and help the other, that you call it as a relay mechanism. In athletics, in running, you might have seen, whenever there is a very lengthy running, 2 kilometer, 3 kilometer running, one person will be running for some time holding a stick. Suddenly they come, there will be another person standing there, they will be giving the stick to them, that person will be holding and running. Such a thing is called as a relay mechanism. So one is augmenting the another one. Okay? Cooperativity is a relay mechanism. Next, when one subunit takes dioxygen, when one subunit takes dioxygen, comma, it stimulates the O2 intake, it stimulates the O2 intake of second subunit Next, these two subunits stimulate the intake of the O2 intake of the third subunit. O2 intake of the third subunit. And finally, the three subunits stimulate the intake of the fourth subunit. This stimulation process is cooperativity. This stimulation process is cooperativity. It was explained by Max Perutz. These points I have explained yesterday. This was explained by Max Perutz. And the mechanism is called as Perutz mechanism. Perutz mechanism or trigger action mechanism. Perutz mechanism or trigger action mechanism. In bracket you write down Max Perutz and Kendrew. Max Perutz and Kendrew got Nobel Prize. Max Perutz and Kendrew got Nobel Prize for giving the X-ray structure of myoglobin. So the structure of myoglobin was known. With the help of myoglobin, hemoglobin is known due to these two persons, Perutz and Kendrew, for which they got a Nobel Prize. Before writing this reaction, just for a couple of minutes you listen to what is cooperativity. Okay? Imagine this as a porphyrin. Porphyrin, it is like a plane. 4 nitrogens you just imagine. Center there is a space. In this space iron can come and sit. But if it is a deoxyhemoglobin, the size of iron high spin is larger than the core. That iron cannot stay. It will come below or above, anywhere. But it is not in the plane of porphyrin. So once it is coming below, imagine this as a histidine. It is attached to a protein. This is one subunit. So whenever it is outside, it is like this. But once dioxygen comes and binds, this is going inside. 2.7 angstroms, this is 2.1 angstrom. So going and coming out. So in this case, the protein is also moving. This protein is attached to the several subunits. We call it as a primary, secondary, tertiary and quaternary structure of hemoglobin. Hemoglobin will have different structures, primary, secondary, tertiary and quaternary. Okay? So this particular protein is attached to some other subunits. This will go and stimulate those subunits. Right? The deoxyhemoglobin, where the iron is outside, this particular state we call it as a tense state. This is like a tense. Imagine no dioxygen, tense state. Okay? So this is like a tense state or T state, capital T they call it as, or taut state. So in this tense state, there is no dioxygen. But once dioxygen comes and binds, this will be relaxed. Iron will be coming into the plane of porphyrin and this state is called as a relaxed state. Tense state, relaxed state. Tense state is unbound. There is no dioxygen. But once dioxygen comes and binds, this will be relaxed. So there is a movement or shift from tense to relaxed. Tense to relaxed. This movement will stimulate the protein part and that will stimulate the oxygen uptake of the second subunit. First and second will stimulate third. 1, 2, 3 will stimulate fourth. This process is called as cooperativity. So two things you have to remember. Hemoglobin is existing in two different states. One is called as a T state, tense state, relaxed state. The movement from T to R, this is called as cooperativity. This is leading to cooperativity. Okay? So there is a small question called as, what is allosterism? Allosterism. Allosterism means existence of hemoglobin in two different forms. T form, R form is called as allosterism. And these two forms are called as allosteric forms. T form, R form are called as allosteric forms. Okay? Hemoglobin existing in two different forms is called as allosterism. The two different forms are called as allosteric forms. These are T state and R state. Movement from T to R is leading to cooperativity. Got the point? You can just note down them. Write the point. This is also related to cooperativity. Hemoglobin exists in two different forms. Hemoglobin exists in two different forms. This is called as allosterism. Allosterism. Steric means anything related to space. Steric means space. Allosterism. Different. Existing in different forms in space. Allosterism. And the two different forms are called as allosteric forms. Allosteric forms. These are one T state, capital T state, or tout, TAUT, tout or tense state. This is nothing but your deoxyhemoglobin. It is in a tense state. T state or tout state or tense state. Second one is R state or relaxed state. Tout and relaxed, T and R. Next, T state is called as unbound state. T state is called as unbound state. T state is called as unbound state. This is deoxy-HB. This is deoxy-HB. Once dioxygen comes and binds, comma, HB attains R state. HB attains R state. It is called as bound state. It is called as bound state. So it is nothing but your oxyhemoglobin. Bound state, oxyhemoglobin. Next, the interconversion between unbound T state, the interconversion between unbound T state and bound R state, the interconversion between unbound T state and bound R state leads to cooperativity. Leads to cooperativity. Leads to cooperativity. Okay, just for your understanding, you look here. This is an unbound T state is converting into bound R state, but there is a group of scientists who have also proposed a different type of state. It is called as a bound T state. Bound T state. It is not there in most of the literature, so don't get confused, but just I am introducing the terminology. If you get anywhere in the literature, you try to study. Unbound is called as T state, bound is called as R state, but before this unbound T state is converting into bound R state, they say that T state is also bound. It means if this is a tense state, in this tense state oxygen comes and binds, then suddenly it will become bound. So that is the meaning of it. It is like a transition state. But most of the literature does not give this. So simply you remember, conversion of unbound T state into bound R state, interconversion is called as cooperativity. Okay. Next point you write down. The Hill's constant. All these are not needed, biological terms, but just remember what is the value of Hill's constant. The Hill's constant for hemoglobin is is n equal to 2.1 to 3.0. N equal to 2.1 to 3.0. 2.1 to 3.0. In human beings, it is around 2.8. It is around 2.8. It is around 2.8. How did you get 2.8? Now did you understand? Hemoglobin is attaching with 4 dioxygens, but all 4 dioxygens are not found at a time. What is the order? It is not 4, but it is around 2.8. So your Hill's constant is nothing but your order of a reaction. You can just imagine like an order. Though 4 oxygen molecules are being involved, if molecularity is 4, but order is only 2.8, that is the meaning of it. How to understand? Now just imagine 1, 2, 3, 4 subunits. These are 4 dioxygens. Okay? First dioxygen is bound, second is bound. When third is binding, one may go out. One may go out. There is a possibility because it is a not strong bond, it is a weak bond. So though there are 4 subunits, all 4 dioxygens may not bind to 4 subunits at a time. When fourth one is binding, suddenly one may go. So average is only 3. In another hemoglobin, there could be only 2 at a time. So whenever I see the average is not 4, but it is anywhere around 2.8. Because when one binds, the another may unbind. So that is the reason, if there are 4 binding sites, all the 4 binding sites are not occupied at a time. The average is 2.8 only. So 2.8 binding sites are only occupied at a time. Therefore, hemoglobin is called as a transport protein. It is not a storage protein. Do you know the difference between a transport protein and a storage protein? Hemoglobin is coming to the lungs, it is taking dioxygen, going to the tissue level, giving away dioxygen. So it is just doing the job of a transport, taking dioxygen, giving away dioxygen. But at tissue level, you have something called as myoglobin. Myoglobin is present at tissue level. That is there only, it will not move. That myoglobin will take up dioxygen, it will store it. And whenever we need, I am speaking now, I need oxygen, that myoglobin is giving oxygen for me immediately. Every time hemoglobin does not come, immediately take up the energy, it will take some time. This will transport. That will go, and that myoglobin it will give away, myoglobin will store it, and that myoglobin will give the oxygen whenever it is needed for respiration. So myoglobin is called as a storage protein, hemoglobin is a transport protein. For transport protein, the binding is not 100%. Whereas for a storage protein, it should be 100%. Only then it will behave as a better storage protein. Okay? So just write down a point now. Final point. In dioxygen binding, though THOUGH, though there are 4 binding sites in dioxygen binding, comma, though there are 4 binding sites in hemoglobin, comma, all the binding sites are not occupied at a time. All the binding sites, SITES, all the binding sites are not occupied at a time. Next, the average occupancy is 2.8. Hence, HB can only act as a transport protein. HB can only act as a transport protein. In bracket, MB, myoglobin, MB has only one binding site. MB has only one binding site which is totally occupied. MB has only one binding site which is totally occupied. Therefore, Occupancy is 100%. Occupancy is 100%. Hence, myoglobin is a storage protein. Hence, myoglobin is a storage protein. Now you can write down these two reactions. You have a bike, only one-seater bikes are also there. You are driving. What is the occupancy of the bike? 100%. Occupancy is 100%. Only one can sit, and while you are driving means occupancy is 100. But suppose if there is a bus, occupancy is 60. Occupancy is 60, but every time does 60 occupy? No. If I take the average from morning to night, maybe the occupancy rate will be 40 or 30. That is the reason they say every time the RTC is in loss, because the occupancy will not be 100%. Okay, so that is the difference. Hemoglobin, though it has 4 binding sites, but all the 4 binding sites need not be occupied at a single time, and whenever I look at the binding, it is anywhere around 2.8. It is not perfectly 4, so it is not 100% occupancy. Hence it can act better as a transport protein. It is not a better storage protein. Finished? Okay, we'll stop with this because at 4 you have some other class, CSIR.